What is nanomaterial and what is nanotechnology? Scale of matter, and we can understand how small the nano range is. There is plenty of room at the bottom. This was a famous statement given by Richard Feynman. A novel materials can be classified on various parameters. Now we will classify nanomaterials based on the dimensionalism. Quantum confinement. Before understanding this thing, welcome to the second episode of the topic nanomaterials and nanotechnology. So let us start. So in the first episode we discussed about the introduction of nanomaterials and nanotechnology, then the nanomaterial terminology and definition, classification of nanomaterials and the effects like quantum confinement, surface area to volume ratio. Now the types of nanomaterials. So there are various types of nanomaterials. We can classify them as carbon based, metal semiconductor based nanomaterials and other. So the carbon based nanomaterials are basically mainly of the 3 to 4 types, such as in the 0 dimension it is the fullerene, in 1 dimension we can say carbon nanotubes, in the 2 dimension it is graphene, and in 3D and also 0D there are various porous type of carbon structures. Now in metal and semiconductor based materials there are thousands of materials. The pure metals are in the nanoparticle state, and the metal oxides, they are also the oxides and also the other sulfides, chalcogenides, they are in the nano structure state. Now the most studied and mostly used nanoparticles are the nano gold and nano silver. Now nano gold and nano silver can be prepared in the form of colloidal gold and colloidal silver. As we had discussed in the first episode that this colloidal gold and colloidal silver were used in the ancient times by the Romans and the Mesopotamian civilizations for staining glass. In the modern times, these colloidal gold and colloidal silvers are used, and they have many type of novel applications. Now the characteristic, the size, they are typically between 1 to 100 nanometer in range, and their shape can be anything between cubes, spherical, elongated, etc. And they exhibit special properties like surface plasmon resonance. So it is a enhanced property of plasma oscillation and resonance occur. Then high surface area to volume ratio. Since the particles are very small, so obviously the surface area to volume ratio will be higher in this type of metal nanoparticles, and they have enhanced and tunable colors, enhanced optical properties and tunable colors due to the confinement effects. And since they have very high surface to volume ratio, they have enhanced catalytic activity and also microbial, antimicrobial activity. Now these two are the TEM micrographs, transmission electron microscopic images. Of the left is the gold nanoparticles, so we can see that the nanoparticles are well below 10 nanometer and the average particle size is 5 to 6 nanometer, and these are the silver nanoparticles. Here also they are of that sub 10 nanometer size, so both of them are actually the quantum dots. Next, the carbon nanomaterials. Now we know that carbon in its sp2 form, that in sp2 hybridized form, the carbon is stable in the form of a hexagonal honeycomb sheet. Now if this hexagonal honeycomb sheet is wrapped in the form of a cage structure, then it is known as the fullerene, and it is 0 dimensional. And 1 dimensional is the carbon nanomaterial, or the sheet is rolled, and when this sheet is stacked one after other, it is the 3D graphite, and the sheet itself is known as the graphene. So we will study graphene in briefly, and graphene, once when it was discovered, it was termed as the wonder material. So why graphene is a wonder material, we will understand from its physical and chemical properties. Now a single layer of carbon atoms arranged in hexagonal lattice, it is called the graphene, because it has come from graphite, which are subsequent large number of layers of the component, that is the graphene. Now the thickness, a single layer of graphene is atomically thin because it consists of a one layer of atoms, and it is approximately thickness is 1/3 of a nanometer, 0.335. Graphene have extremely high strength, flexibility, and its tensile strength is very high. It is much more flexible and strong than the highest grade steel, and yet it is much lighter than steel. It is optically transparent. Obviously, it is so thin, so graphene is optically transparent, and obviously it should have high surface area. And the chemical properties, although graphene is one atom thick, but still it is chemically inert at ambient conditions. Functionalization is a very important property, that the various chemical properties of graphene can be easily tuned or manipulated by functionalizing the bonds with some functional groups. The reactivity of graphene can also be tuned with functionalization and various other chemical modification. Synthesis, there are various types of synthesis, such as the mechanical exfoliation, which is the scotch tape peeling method, chemical vapor deposition, then epitaxial growth, and one important chemical synthesis, that is the reduction of graphene oxide. It is very popular, known as the modified Hermann's method. Applications, the graphene have lots of applications in electronics, that is the transistor, flexible display sensors, and energy storage devices like the supercapacitor and batteries. It have applications in various type of composites, which adds strength and flexibility and also electrical conductivity to the material. It have applications in the biomedical field for drug delivery, tissue engineering, and it have environmental impact, environmental applications such as the water filtration and the removal of pollutants. And in energy field, as I discussed earlier, it have applications in fuel cells, batteries, solar cells, as well as supercapacitors. Now let us come to the carbon nanotube. Now we can see in this animation that a carbon nanotube is basically a rolled graphene sheet. Now it have many similar physical properties like that of graphene. These cylindrical structures are made up of rolled graphene sheet, and they have high aspect ratio, high strength and flexibility. So the excellent electrical and thermal conductivity, high strength and flexibility, they are similar to graphene, but they have the high aspect ratio, that is their length is much longer than their diameter. The chemical properties, just like graphene, they are also inert under ambient condition, and like graphene, they can be functionalized with various functional groups, and also the chemical reactivity can be tuned. Synthesis, carbon nanotube can be synthesized by arc discharge method, laser ablation and chemical vapor deposition, and it have applications just like graphene. It has applications in the composites, in which it adds strength and flexibility and also electrical conductivity. It have applications in the electronics, especially the transistors and sensors. Similar to graphene, it have application in the energy field like battery, supercapacitor, fuel cells, and in the biomedical and in the environmental field also. So both graphene and CNTs are very promising materials, and many work already has been done with the use of graphene and carbon nanotubes, but still researchers are continuously progressing, and many more novel works are yet to come with these materials. Now metallic oxides. Now in the nano field, there are thousands and thousands of metallic oxides. So we will only discuss the two representative metallic oxides which are the most widely used or most widely synthesized and have applications. One is the titanium dioxide and another is the zinc oxide. Now both titanium dioxide and zinc oxide have a certain similarity in properties. So let us discuss briefly about titanium dioxide. Now titanium dioxide mainly exists in two crystallographic phase such as the anatase and the rutile, and a less popular, that is the bruchite. So in appearance it is a whitish powder, that is the anatase, and the rutile and the bruchite, they are the reddish brown to yellowish. And the crystal structure, the anatase is tetragonal, the rutile is also tetragonal, but the bruchite is orthorhombic. So it is a different phase of the tetragonal. Now the band gap is about 3 to 3.2 electron volt, so it is a wide band gap semiconductor. And TiO2 exhibit photocatalytic activity, so it has already been proved that titanium dioxide is a very good photocatalyst, but since its band gap is wide, so it is more active in the ultraviolet region. Chemical properties, it is stable and it is amphoteric, means it can react with both acids and bases, and it is self-cleaning. And applications, they are used for pigments, photocatalysis, solar cells, cosmetics, and other type of catalysts, sensors and cosmetics, etc. Another widely studied metallic oxide is the zinc oxide. The zinc oxide exists in mainly two phases, that is the cubic zinc blende and the hexagonal woodsite. So zinc oxide appears white in color, and its band gap is also a little higher than that of the titanium dioxide. So it is about 3.37 electron volt, and it is a direct band gap semiconductor, and since it is 3.37, so it is a wide band gap semiconductor. And another important property is it has some piezoelectric properties, and also it is a good photocatalyst. The chemical properties, like the TiO2, it is amphoteric, and it also has some antibacterial properties apart from the photocatalytic activity. Now they are used in sunscreens, pigments, sensors and other types of catalyst, and even in food additives, because zinc oxide is not harmful for the human digestive system in small quantities. Now we will discuss about the properties of low dimensional materials. So in the first episode I discussed that when the particles or the nanomaterials are in the low dimension, then various new properties emerge which are much different from the bulk, and also the bulk properties are radically modified. So here we will discuss about the new emergence of properties such as the change in the physical, mechanical, thermal, electrical, optical and magnetic properties of the nanomaterials. So here first we will discuss about the physical and optical properties. So the color or the appearance. Now we have seen that bulk material and the nanomaterial of the same element of the compound, they looks different. For example, bulk gold is yellow in color, whereas nano gold colloid appears red. So this is due to the quantum confinement effect, and that can be explained by the discretization of the energy bands when there is the reduction in the size of the particle. Next, the mechanical properties. Now let us discuss about the mechanical properties of nanomaterials. We know in nanostructures or nanomaterials the particles are of very small size, and as we go to the nano dimensions, there is increase in the number of grain boundaries as well as the surface to volume ratio increases, and so some new emerging properties develop. For example, the elasticity of the nanomaterials is different from that of the bulk. In bulk, the materials follow the Hooke's law up to the elastic limit, that is, the stress is proportional to strain. But in case of nanomaterials, it does not happen always. There is generally a nonlinear relationship in nanomaterials between the stress and the strain, and so we can say that nanomaterials doesn't always follow the Hooke's law. Hardness and ductility. Yes, when the particles are much smaller in size, so they are composed of many particles that are stacked together, so the grain boundaries are the amount of grain boundaries is larger, and also the exposed surface is also greater, and so there are some complex phenomena, elastic properties can occur. Generally, the hardness of a material increases in the nanoscale, whereas the ductility of the material reduces. A metal in the bulk is ductile, that means it can be easily drawn into threads, that is very thin structures, but in the nano the material can become brittle, and this can be explained with the help of the yield stress. Now it has been observed that the yield stress increases when the particle enters in the nano region, and this systematic study was done by the Hall-Page and Page, and it is given by the Hall-Page relation, which describes the yield stress of the nanomaterials with the yield stress of the bulk, and it is a function of the size of the particle. Now let us come to the thermal properties. The melting point of bulk materials generally does not change with the size of the structures, but when we come to the nano region, then there is a change in the melting point. Now the melting point of nanoparticles or the nanostructures are generally lower than their bulk counterparts. The reason of this lower melting point is due to some breakdown in symmetry of the nanoparticles, because when the particles are in the nano region, the number of surface atoms are much larger, and so there are a tendency of higher thermal vibrations for the same amount of thermal energy, and as a result the materials come to the liquid state at a lower temperature, and hence the melting point reduces in the nanoscale. So here we see an experimental observation of the observed melting point in degree centigrade, and this is the diameter of the gold particle, and we see a decreasing trend of the gold melting point of the gold nanoparticle as the particle size reduces. Another thermal property is the specific heat. Now specific heat is inversely proportional to the grain size, that is, if the grain size reduces, then the specific heat increases. This can also be explained in terms of the particle size. Now if the particle size are small, then there are more grain boundaries, there are more tendency of defects, and so that material can retain much more heat for the same change in temperature, and as a result the specific heat of the materials increases with reduction in the particle size. Thermal expansion. Now the thermal expansion coefficient also increases with decrease in the grain size. Now this also can be explained due to the various bonding energies and the vibrations near the surface, because the surface atoms are much larger in number in case of the smaller nanoparticles. And here we also see the thermal expansion coefficient of some material which is plotted against the size, and we see when the particle size is smaller, the thermal coefficient increases. Electrical properties. Now this is a very interesting property observed in the nanomaterials. Now in bulk, the electrical property of the materials generally does not change with the size or shape of the conductor or the semiconductor, but in the nano there is a general tendency of decrease in the electrical conductivity when the particles are in the nano range. Now this can be explained by two phenomena. One is the quantum effect and another is the classical effect. Now in the quantum effect, it is due to the discretization of the energy bands, and we know that due to discretization, especially the semiconductors, the band gap increases, and if the band gap increases, then the conductivity will decrease, because proportionately more energy should be required to place the electrons from the valence to the conduction band. And the classical effect is the mean free path. Now when the particles are very small in size, there will be more scattering of the particles, and as a result the mean free path will decrease, and larger the scattering, larger will be the dissipation of energy, and so the resistance of the material will increase, and that is the electrical conductivity will decrease. So we can say that both due to the classical effect and quantum effect, there is a decrease in the electrical conductivity as the particle size increases. And now we come to the magnetic properties. The magnetic properties of the nanomaterials can also drastically change. For example, if we consider various magnetic properties of the bulk and the nano, then various type of ferromagnetic materials, we know that in the bulk form they are composed of large number of domains, but when we make them in the nano, then it may happen that it is a single domain. So a material, a single nanomaterial, nanoparticle is existing as a domain, and what is the net result? It is the increase in the magnetic moment, because all the magnetic dipoles are oriented in a same direction in the one particular domain. Also, occurrence of superparamagnetism in various small ferromagnetic particles. So there is a lot of theory of superparamagnetism which we can explain in the nanomaterials, but those advanced theories are beyond the scope of this present lecture, so I will not explain the physics in depth about it, but we can say that superparamagnetism is a phenomena which occurs in the small nanomaterials, and giant magnetoresistance effect occurs. So magnetoresistance is what? When a material is placed in a magnetic field, then their electrical resistance increases, and as we decrease the size of the particle, the giant magnetoresistance effect also increases. Then some of the antiferromagnetic particles behave like ferromagnets. So these are some of the observations. We will not go into the main explanation of the magnetic properties. Now the net result of all this effect is that the magnetic moment of the nanomaterials increases as the particle size reduces. Now novel materials. Now using nanotechnology, the fundamental physics of nanomaterials, we can develop various type of novel materials, and among the novel materials, the smart materials are very important because they are the materials of the future, and many materials have already are being used in the present times. So what are smart materials? So smart or intelligence material are those materials which can react with some change in the stimuli of the environment. So they can adjust and react themselves according to the environment. So various examples of smart materials are the thermoelectric materials, the chromogenic, the electrostrictive, magnetostrictive, piezoelectric, and the shape memory alloys. So let us discuss in brief about these materials. Now the piezoelectric, this is a smart material. So piezoelectric materials, they convert electrical energy to mechanical energy and vice versa. Now all piezoelectric materials may not be nano. There are many materials which in bulk state they also exhibit piezoelectric effect. So, but in the nano range, the piezoelectric properties may be much more enhanced. Then shape memory alloys. What are shape memory alloys? For example, there are certain types of alloys of metals. If it have a certain shape and we just apply force and change the shape and then it is heated, then it regains its original shape. That means it have the memory how its shape was previously and it comes back to its original shape. Now let us discuss about the magnetostriction. Now there are certain materials which can respond to magnetic fields. So some mechanical energy can occur due to some magnetic fields and they are analogous to the piezoelectric materials which convert electrical energy to mechanical energy. And the next smart materials is the hydrogels. So the hydrogels are a special class of materials which are made up of various nano components. Then comes the electroactive polymers. Now the electroactive polymers are a special class of polymers like polyvinylidene fluoride. These materials have a special property that they can undergo swelling, shrinkage, bending in response to electric field due to some structural deformation and also change in polymorphic phases. Chromoactive materials. Chromoactive materials are the materials which can change color due to certain environmental changes like change in temperature, light and pressure. Now let us see what are the applications of these materials in our day-to-day life. This we know that this is a gas lighter. So there is some gas, LPG gas is there, and when we push this button, then the light, if the flame comes. Now how this happens? Previously some spark was produced in this type of lighters by rubbing with a material. It produced sparks. But in the modern times we use piezoelectric materials in which if we apply a certain mechanical force, then an electric voltage is developed, and this electric voltage in this piezoelectric element can be so large that it can just produce some electrical spark between two terminals by breakdown of the voltage, breakdown in the air, and this spark can ignite the gas. Now this is the thermochromic pigments. Now we have seen that in various gift shops, in various items, we have seen that these are some of the cups, coffee mugs in which when hot coffee is poured, then the color changes. This is due to that thermochromic materials which changes color when the temperature is changed. Then these are the hydrogels. So these hydrogels have many type of applications in the medical field, in some decorative purpose and many other field of chemical synthesis also. Now another application of photochromic pigments is the day and night glasses. Now we have seen that in the coffee mug, when the temperature is changed, the color changes, and here due to change in intensity of light, the color can also change. Now if this type of photochromic pigments are used in the glass of the specs, then when the outside light is of very high intensity, then it can turn a darker shade, and thus it can be applied in day and night glasses. So this is an advertisement. So in indoors, when the light intensity is less, it is transparent, but in outdoors, when the light intensity is high, it becomes dark. Now this is one picture of the shape memory alloy. This is the original shape of any material. Now it is deformed by applying some force, and it remains deformed, but when it is heated, then it also regains its original shape. For example, you might have seen some video in which there is a spring. Now the spring is just deformed and it becomes into a knot-like structures, and it cannot be just made into the original shape, but when it is heated in a pan, then it regains its original shape because it is made up of a shape memory alloy, and that alloy is known as the nitinol. And this is a illustration showing various types of applications of other smart materials in the medicine, and there are the actuators, sensors, pressures, for example pressure sensor, light sensor, and for the environment using the electric and the magnetic fields. Let us discuss about the health risks of nanomaterials. Now, throughout the lecture we have discussed about the applications and advantages of nanomaterials, but on the negative side also there are some potential disadvantages and dangers of using nanomaterials. Now, there are various type of health risks associated with this type of small particles and the nanostructure. For example, inhalation risk and the dermal exposure. Now, the nanomaterials are so small in size that they can move at any place and we cannot see them, and also they can disperse in liquids and air. So the nanoparticles, for example, someone working with carbon nanotubes or very fine nano powder, it may get dispersed in the air, and inhaling that air can be dangerous and it can produce many type of health risk. Similarly, our skin have pores which are large enough so that the small nanoparticles can go inside our body through the skin, and there can be some potential danger if these nanoparticles are harmful for the inside of the body. So they can react with the blood vessels, they can react with the body fluids. Similarly, ingestion. If accidentally the nanoparticles are ingested, whether through some liquid or some food, they can also pose danger for our digestive system. Very small nanoparticles are highly reactive in nature, and so if they enter in our body, they can produce some chemical reaction, and they are toxic for both the nerve cells as well as the body cells. So potentially many nanoparticles are neurotoxic and cytotoxic, and there are some potential risk with the environment also, because certain nanomaterials which are used for water purification and as nano fertilizers, they can produce detrimental effect to the environment. And last but not the least, carcinogenic. Many nanomaterials can induce cancer in the human body because they are highly reactive and they can indulge with the biological process of the cells, and they can be carcinogenic. So these are some of the potential dangers and perils of nanotechnology. So measures should be taken to work carefully with these nanomaterials, both in the laboratory as well as outside. So protective gloves and protective clothing should be used, and also education to the general public should be imparted for the growing increase of the use of nanomaterials in the environment. And with this, I conclude the second and the final lecture on nanomaterials and nanotechnology. Thank you to all of you.